Okay, I guess probably we can start. So today we have Michał Godziszewski from IDEAS Research Institute in Poland, and so he will tell us about Stackelberg Games. And I just want to mention that like any your comments in the end will be so Michał will be more than happy with them with like any suggestions on uh like any applications in context of AI or what you will hear on. So I mean, feel free, and yeah, and I guess we could also have some small questions during the talk, especially from Zoom. So I guess, Michal, I guess you can start. So please go
Okay.
ahead.
Thank you so much. Thanks for the invitation. I'm really honored to speak at this seminar. And as you mentioned, I will be speaking about Stackelberg Security Games in AI. This is joint work with my boss Tomasz Michalak and my colleague Andrzej Nagurko, done in our capacity as researchers at IDEAS Institute. And to give you a short outline, first I will give an introduction, then introduce Stackelberg Games and its application to the model of security games, where I'll perhaps be a little bit more formal, but just for a couple of slides. The main goal of the talk is to convey the main idea and why it is possible to apply Stackelberg Games in security domain. So most of the talk will be largely informal. However, I hope I will not bore those who perhaps are even experts in game theory or related fields, and will have something to talk about. And then at the end, if time permits, I will introduce the model of the so-called two-phase attacks Bayesian security games, which is something that our team at IDEAS came up with, and that we are hopeful that will be able to be developed and applied in real life scenarios quite extensively in the nearest future. And if during the Q&As you have some formal questions concerning some complexity or more general computational issues, then I think to some extent at least I should be able to discuss that as well. So without further ado, let's get to introduction. And as I said, I will keep most of the stuff very, very basic. I believe that's useful, even if somebody might think these are too fundamental and easy stuff, just to make sure that everybody's on the same page. So as you perfectly know, game theory is a branch of math stolen part-time by economists that studies interactions between entities that are intelligent, like individuals, companies, or nations. And in context of security, especially in the context of protecting things like critical infrastructure of states, those, I mean, states like Poland, Chile, Spain, not the United States specifically. Those entities can represent different items and subjects, such as security forces, police, military, and other defenders of various resources. And we can also have attackers, such as criminals, terrorists, or other state actors in particular applications. And the reason why game theory is so useful, it can be an aid in understanding how interaction between those subjects takes place, assuming, of course, that we somehow anticipate and respond rationally to each other's actions as those subjects. And by using game theory and adding to it some algorithmic considerations, we can develop strategies to distribute some scarce security resources for infrastructure protection. The most popular example that I will not dig into perhaps is the application of the work by Milind Tambe and his group during their time at the USC, where they applied an algorithm based on a Stackelberg Security Game solver for distributing resources for patrolling multiple terminals at the International Los Angeles airport with a lot of success. I will mention another example though during the talk. I will not speak about the armor system at the Los Angeles airport because it's so popular, but I will speak about the application in New York and Boston Coast Guard services. So again, to make everybody on the same page in terms of easy formal aspects. So by a non-cooperative, because we will discuss only non-cooperative games, we mean a tuple that is defined by the set of players, the set of strategies for each player, and utility function that gives the payoff for any possible combination of strategies. And additionally, our games can also have rules, and those rules are usually formalized in terms of the notion of equilibrium that will be applied in particular situation. So we can, for instance, require the players to move simultaneously or sequentially, which will be interpretations of how equilibria are defined. So to introduce the easiest, to recollect the easiest solution of equilibrium, let's consider the following game. We have two players here, the row player and the column player, and the row player can choose to play a move called row 1 or row 2, and this will be their strategies, and the column player can choose to play column 1 or column 2. So R1, R2, and C1 and C2 are the possible choices of strategies for both of the players. And here in the entries of this easy matrix, we have the payoffs for both of the players, assuming that a given strategy or a given move is chosen by given players. So in here, in the first entry, in entry 1-1, we have the payoff that says that if the row player chooses to play row 1 and the column player chooses to play column 1, then the payoff of player 1 is 2 and the payoff of the column player is 1. And if we have row 1, column 2, then the payoff of the row player is 4 and the payoff of the column player is 0, etc., etc. So this is an easy game, and we can perhaps stipulate how the players actually would play the game given its rules. So for the moment, assume, as it is in classical and basic game theory, that the players actually move simultaneously, i.e. they know the payoff matrix of the game, but they don't know the actual choice of the other player at the moment of taking their own decision, and they have to strategize by anticipating what the opponent would do. Informally speaking, how the players would actually play the game given its rules is usually called an equilibrium, and there are many types of equilibrium. So let's discuss first the Nash equilibrium. So the game hasn't changed, it's still the same game as then on the previous slide, and the most popular notion of equilibrium is Nash equilibrium. And informally speaking, we would say that a combination of strategies so an equilibrium is always a combination of strategies. It's a Nash equilibrium if it is such a combination that given the strategy chosen by the opponent, any player wouldn't like to change their strategy. They don't have an incentive to deviate from the given combination of strategies, assuming that the other player will play the strategy at this given point. So for instance, when we look at the strategy row 1 and column 2, which gives the players payoffs 4 and 0, then it is easy to prove that this cannot be Nash equilibrium, because when we take a look at the column player, then assuming that the row player chooses to play row 1, then since here the column player obtains a payoff 0, then they have an incentive to switch, to deviate from playing C2 to C1. So this is in a certain sense an unstable solution of the game for the column player. So assuming that the row player sticks to the strategy row 1, the column player wouldn't like to stay at the C2 strategy. They would rather play the C1 move, right? So they would deviate. But speaking of which, the R1, C1 actually is the Nash equilibrium of this game, because when you assume the column player that it plays the first column, then the row player is better off if they play R1 instead of R2. And assuming that the row player plays R1, as we argued before, then C1 is preferred by the column player. So this, in this sense, is the Nash equilibrium of the game. And this is the most popular notion of equilibrium, most widely applied. But if we change the game, sorry, so before I switch to other notions of the notion of equilibrium, let me give you another information about more complicated Nash equilibria. So if you consider the same notion of equilibrium but in a different game, then you can easily see that there are games where there is no pure strategy Nash equilibrium. In here, for every pair of strategies, one of the players has an incentive to deviate from this given combination of strategies, assuming that the other player. Sorry. For each combination of those strategies, there is a player such that they have an incentive to deviate from this given combination of strategies, provided that the other player sticks to the given strategy. So then we say that there is no pure strategy Nash equilibrium, but by the famous Nash theorem, for every game in such a normal form, there exists a Nash equilibrium in the so-called mixed strategies, where rather than committing to a particular move in your strategy, you commit to a probability distribution between the moves that are available, right? So instead of playing a particular row with probability 100% and the other with probability 0, you can distribute the probability of playing those two moves. So actually, with omitting the necessary calculations, the optimal solution for both of the players in mixed strategy Nash equilibrium is that when the row player chooses the first row and the second row with equal probabilities 1/2, and the column player with probability 2/3 and column 2 with probability 1/3, it's easy to compute that then the expected payoff of both players is 5/3 and 3/2. And this is the distribution from which no player has an incentive to deviate. And in this sense, it is also a Nash equilibrium, but with this additional possibility of having non-zero or non-unit probabilities for given strategy, for given moves in the game. Right, but when we consider possibilities of applying game theory in security domains, then one might say that the way we usually interpret the play of the game given by the notion of Nash equilibrium is in some sense inaccurate, because the players basically do not move simultaneously. So for instance, when we decide to distribute our patrolling services to given times and given spaces in a given place, such as an airport, then we do commit to such a distribution, and then our opponent, possibly a terrorist or a drug trafficker or whatnot, can observe what we are actually doing and then make another move, and then we can observe it and make another move, and so on and so on. So it's not even an iterated game where we make simultaneous moves. It is rather a game where the moves are played in a sequence. And thankfully, there is a nice notion of equilibrium that takes that into consideration, takes into consideration the fact that we might be able to observe what kind of, say, defensive measures, as the ones that I described, are employed by a player who is a defender. So there is this seminal economic model that was proposed by the German mathematician Stackelberg, and a game with Stackelberg equilibrium is played by two players, and one of them is a leader and the second one is a follower. And the thing is that the leader commits to a certain strategy at the beginning, and the follower can observe that. To be a little bit more precise, because informally you might say that this means that the game is played sequentially rather than simultaneously, but strictly speaking is a little bit more complicated. So the leader selects their strategy, and their choice of the strategy is basically observed by the follower, who then determines their own move accordingly. And then the notion of equilibrium is kind of the same, but by the fact that you can interpret this as the game being played in another way, a particular combination of strategies that are chosen by the players in the state of equilibrium might differ. And one small technical thing is that in such case, when we compute the best strategy, so for formal reasons, to have a mathematically well-defined notion of optimal solution, we break ties in favor of the leader, in the sense that if we have two possible mixed strategies for the follower, that give them the same payoff, i.e., if the follower is indifferent between a choice of strategy S and T, then if S is better for the leader than T, then S goes into the equilibrium, right? So otherwise, actually, we would have problems with defining the optimal solution. But aside of formalities, the important thing is that there are certain parts of the dynamics of security domains between the defender and attacker that are actually well encompassed by the model of Stackelberg games. So first, when we take the defender, this will be our leader in the Stackelberg game. Then, as I said, we allocate some limited security resources to protect some set of targets. Right, you can think of policemen protecting, I don't know, certain rooms or certain buildings, and you don't have as many people to protect them as there are the buildings, so you have to somehow distribute it, and then maybe you might want to change that, etc., etc. And now the thing is that you can recognize that your adversary might be able to observe where you stand or which targets you decide to protect. So it seems natural that you would opt for a mixed strategy so that the opponent doesn't see what you actually do, but can only observe a frequentist sample of your plays. And then the attacker, who is the follower in the sense of Stackelberg game, can see what your strategy is, i.e. can see your probability distribution, because we simply can presuppose an attacker who basically does a thorough surveillance before doing anything in the sense of attack. And now, the attacker, when they learn the probabilities that are selected by the defender, they strategize and they choose the optimal course of action for themselves and execute their move accordingly, right? And what is crucial, what I'd like to underline, is that when you are the attacker, you are able to observe the probability distribution chosen by the defender, but not the particular move from that probability distribution that you can see. So you don't play simultaneously in a sense. I mean, sorry, that you do play sequentially, but it's not the case that you can see what the defender is actually doing and then choose what you do, but you can see only the distribution of what's going to happen before you play. So, right, it's not the case that the patrol has been put between targets T1 and T2, so I can see that the target T3 is unprotected, so I attack T3. No, I know the probability distribution between T1, T2, and T3 by surveillance, and now I have to make my move, and the play will be played after that. This is the part in which I would like to underline that this interpretation of sequential choice of moves might be misleading, right? So it's the observation of the strategy, the possibly mixed strategy of the leader that the leader committed to. So this is something that the attacker or the follower can see. And as an illustration, we can consider this is the example that I mentioned. I would describe a little bit. So when we have U.S. Coast Guards, then their idea for patrolling the Mexican Bay to combat drug trafficking has been actually applied in wider domains. And this is a particular example of something that is well modeled by Stackelberg Security Games, since the smugglers can observe the statistics of the patrols in specific areas and how frequently the boat change their course in the patrol. So they can compute something, but they only see the probability distribution in a sense. I mean, they see the sample from which they extrapolate, but they cannot see what particular move will be done by a particular patrol in a particular moment, right? So they cannot predict whether a boat will change its course from patrolling this particular region to another at a given moment or not. So in a sense, you cannot wait. That is exactly the sense in which I said that you commit to this strategy as a defender, then an attacker chooses by seeing what's the defender committed to, and then you play. Right, so you don't have a total freedom as an attacker here, and this is something that will give the defender a real advantage. And actually this is another application done by the same research team that I mentioned about with reference to the LAX airport. And the thing is that it's been also applied by the Boston Harbor Services and US Coast Guard, protecting the famous Staten Island ferry in New York City. So there is a software system called Protect that basically has an algorithm based on solving Stackelberg games, and they actually use it practically as we speak to enhance the security of the Staten Island ferry boats. So the US Coast Guard basically in this model patrols and there are not as many boats as to be able to protect the boat from all of the sides. So they actually have to change their course, and the way they change their course is done through a certain randomization that is given by the software system that has built in a solver of Stackelberg game with that particular security application in mind. So it's been deployed to protect the route of the Staten Island ferry. And it's exactly the attacker-defender Stackelberg game model, but in a particular setting where you don't have like 7 buildings and you distribute the resources, but you have a moving target and you have to change the course to be able to patrol it in as much time as possible. And a nice thing about it that I am not and will not mention in this talk, because it's another degree of complication, but it's also being deployed, is that those application systems, they do not assume that the adversaries possess perfect rationality. So you also have this model that additionally put a layer of restricted rationality of the opponent for the application. Okay. And now, after this description, you might think that, in a sense, when you are a defender of a critical infrastructure and you try to model the situation by the use of Stackelberg Security Game, then you are at a certain disadvantage because basically your opponent can see everything. You're being observed by the attacker, and therefore they have a handicap or something. And actually, it's quite the opposite. So since you are the first mover as a defender, you can have a significant influence on what will be rational or optimal choices that can be made by the attacker. You can severely restrict or retarget the possibilities of strategist choice by the attacker, and therefore this can put you in a privileged position in the game in a sense, right? So you can push the attacker to choose one strategy and not the other. So let's consider the following game. Right, so we have again the row player, the column player. We can observe what would the Nash equilibrium be, and we can try to compute what would be the Stackelberg equilibrium mixed strategies, and let's look at that for a moment, right? So we can see this game, and when we think of Nash equilibrium, right? So think of this interpretation that you move simultaneously without then committing to any strategy. Then the only Nash equilibrium of this game is row 1, column 1, right? You can see that if you have this, then obviously the row player doesn't have an incentive to move, provided that column 1 is being played by the column player, and the column player doesn't have the incentive to move to column 2 because they win something if the row player plays the row 1. And this is not the case for any other strategy. So the only Nash equilibrium in here is this one. So whether it's in mixed or pure strategies, this will be and basically trivially every mixed Nash equilibrium strategy will be a pure strategy where the distribution is simply trivial. And the row player has so look at the defender, look at the leader. the role player, let's consider the change of setting where you would have the role player that is playing the role of the leader, and they would be a defender of some security resources, and they would be able to commit to some kind of mixed strategy. Before considering that, you can see that the role player actually has a payoff equal to 1, and that's it. And now consider them playing in this Stackelberg framework. If you are able to move first in the sense of committing to a strategy that will be observed by the opponent, then you might actually be much better off if you choose a mixed strategy of playing both rows with probability 1/2. In such a case, then the column player actually, contrary to the situation with Nash equilibrium being the solution concept, changes from C1 to C2. Now you might think at this moment that, wait a minute, there is no difference for the follower or for the column player to play either C2 or to play C1 and C2 with equal probabilities. And that would be true in the sense of expected payoffs. It would be 1 it would be the same in both cases. But the thing is that, as I said, there is this formality that if the follower is indifferent between two solutions of the game, then we break such a tie in favor of the leader. So if the role player chooses the mixed strategy of playing R1 and R2 with probability 50% each, then you can see that actually the column player is much better. So if they played only C1, then basically they've got 1/2, right? And if they play C2, they are better off. And the thing is that in such case, the role player can actually secure the expected payoff to be 2.5 instead of 1, right? So, which is in terms of games a huge difference for the role player. This is only by the use of this committing to a strategy at the first place. As a side note, actually here, observe that if you had a pure strategy of playing just R2, then this will give them only a payoff of 2, which still would be better than the payoff in Nash equilibrium, but it's worse than the expected payoff in mixed strategy. So not only can Stackelberg equilibrium privilege the defender, but the mixed strategy Stackelberg equilibrium can be better than if we only allowed for pure strategy Stackelberg equilibrium, right? So now a little bit of formalities, if I may, to be more precise, how exactly we model that. So basically a security game will be a 2-player game that has a defender and attacker as the players. And we assume that the defender has some security resources and wants to allocate those resources to protect end targets. And now a pure strategy is simply a subset of targets that is protected. So here I will be introducing the application of Stackelberg model to the particular setting of security games. So usually people change those names, but the strict order should be that there is the Stackelberg model of a game, i.e. the games in normal forms with Stackelberg equilibria, and then you have security games where you have some targets to protect, and then Stackelberg security are the security games with Stackelberg equilibrium, and this is how we'll reason about it. Right, so you can cover some of the targets, and so your pure strategy is basically a binary finite sequence, right, where you have covered targets denoted by 1 and uncovered denoted by 0. So the set of your pure strategies will be some subset of those sequences, and basically the mixed strategy of the defender is basically the probability distribution over the elements of the set of allowed pure strategies, where the attacker pure strategy we assume is simply 1 target. So in the simplest model, this can be then complexified, but in the simplest form, the attacker can choose 1 target to attack, and the mixed strategy is basically an n-dimensional simplex. where you can have a probability distribution over which target to attack. And if the target is attacked and are protected, then the attacker will gain some reward. And if it's unprotected and unattacked, nobody gains anything. And if it's attacked but protected, then the defender should be better off. And this will be formalized a bit in a moment. But in general, when we have those games, then we can actually define them formally by a pair of matrices and a pair of abstract polytopes. And given that the player plays a strategy from the polytope, so this will be the spaces of strategies, and this will be the payoff. So given that the player 1 plays some strategy and the player 2 plays some strategy, then you have the utilities that are given by the matrices in A and B. So you basically multiply the strategy by the matrix by the strategy of the second player, etc. And now the strategy profile will be a Nash equilibrium if exactly what I described will happen for any choice of the strategy of player 1. If this X prime is played together with Y, then X from the Nash equilibrium with Y makes the first player better off, and the same goes for the second player. So this could be actually given by a conjunction of two conditions, and the same goes for the second player. And as I said, in any bilinear game, there might be many Nash equilibria in mixed strategies, and there is always at least one Nash equilibrium in a given game. And now, when we have one player moving before another or committing to a strategy before another, which would be perhaps a more precise way and more accurate way of phrasing this, then we have a more appropriate solution concept of Stackelberg equilibrium. So the leader commits to a mixed strategy, the follower observes the leader's strategy and then responds in a manner that is best for them. And then the leader's optimal strategy together with the follower's best response is an equilibrium, right? So when we have the payoff of the follower, then what maximizes it with a given strategy X is the follower's best response to a given leader strategy X. So a given combination of strategies is a Stackelberg equilibrium if X is a maximization, gives a maximization of the payoff for the leader given the best response of the follower, right? And the response of the follower is made provided that they see the probability distribution of the strategies of the leader. Right, and actually the thing is that when your game is zero-sum, which formally in this bilinear games translates to the fact that one matrix is simply a result of multiplying everything in the first one by -1, then those equilibria are actually equivalent to minimax equilibrium. And minimax equilibrium gives you basically the same definition. You just replace one of the matrices by B, and you put the minus sign in a proper place, right? And then you have a maximum strategy of one player and minimax strategy of the other player, and you can very well define a unique value for a zero-sum game. And now the payoff structure for the security games is as follows. If when we assume that the attacker attacks a particular target, then the defender gets a particular reward if they are able to, if they, by what they play, they cover or protect the target, or they have a cost if it is uncovered and attacked. So they lose, basically, the attack is successful then. And then for the attacker, it's the other way around. If you attack a target that is protected, then you get a cost, or you get a reward if it is uncovered. And for all the unattacked targets, you have utility 0, which might be considered to be a little bit unnatural assumption, in the sense that if you employ some resources for protecting some targets, but they are not attacked, then it doesn't seem that your utility is zero. But then one might argue back that, well, maybe they weren't attacked because you protected them on some sense. So we decide to put 0 over there. And the assumption is that the reward is greater than the cost, and that that goes for both of the players, i.e. covering the target is beneficial to the defender, and the attacker prefers to attack the target when it's uncovered, basically. And now, formally, to end this matter, the security game is simply a tuple of reward, cost, and the space of strategies, because everything else is being defined over that, right? Right, the Stackelberg equilibrium is a solution concept that you can define that might be better for the security applications. And computationally speaking, the goal of solving the games is to compute the mixed strategy for the defender to commit to. But it's also important to remember that there are situations where you might want to move to Nash equilibrium. So it's not like, okay, let's drop classical normal 4 games with Nash equilibrium. There might be situations where the surveillance is not being done, where you can have some type of a blitz attack that cannot be, for some objective reasons, prepared with a thorough surveillance. But sometimes you might not be able to observe the strategies due to limited resources, etc. So then you actually want to compute some best or worst Nash equilibrium. So computationally, this is what also people do in these cases. And if I may cross the time a little bit, I would like to say just a couple of words about the thing that was developed in our team, the so-called two-phase Bayesian Stackelberg Security Games. So usually the attack is being modeled as one assault, during which the attacker doesn't update their strategy, even if they obtain some new information, which actually seems unrealistic, especially in the current world of very agile actors that perform in security domains. And we actually have a model that in the first phase you have the attacker that makes the preliminary move that is particularly and specifically designed to obtain some new information about defenders' activities. So it's like a additional part of surveillance, but being done with already making a move in a play. And then in the second phase, you choose an optimal adjustment to the first move, provided the information that is obtained by this first move. And the real world example that I would like to share is that basically the situation on the border between Belarus and Ukraine. This can be, I mean, this was in a sense even inspired by that example, because that's the tactics of the Lukashenko's regime. So the thing is that this action puts why it's useful and why you want to consider that is because the lives of people basically are in extreme danger, and that's simply serious. That's not an overstatement typical of some applications, but it's really the case. And the thing is that the border is very long, heavily forested, and it has wetland and the exclusion zone in the middle. And it was crossed by the Russian army last year, restored by the counteroffensive, and now it's fortified with trenches, walls, and minefields. So actually, it is a difficult terrain where some additional actions can be taken into consideration. So even if you have some electronic security measures, you can and you can detect the border crossings that are being done by the opponent, then this doesn't mean that you can guarantee that you will have a patrol that is close enough to prevent the entry, or to have the people to be able not to run over the forest, but to apply for asylum somewhere, right? I mean, regardless of interpretation, if you make your border if you don't make your border impenetrable, then stuff can happen. And then even if you have the section of the border that is unguarded at the moment of entry, then you only dispatch a team to the area. This is what Ukrainian headquarters do. And then the subsequent attempts to enter the same section are highly unlikely to succeed by the fact that the response is quite swift. So this seems to have the structure of exactly the model of those two attacks that are being done in two phases. So just a scaled down version, basically, to conclude the talk. So imagine you have 4 sections of the border and you have 2 patrol units, and the sections of the border can be crossed in any way, but you can observe only the two of them, right? So you can easily model that by a security game. So your pure strategies as a defender are possible assignments of 2 patrols to the sections of the border, right? So you have 6 pairs of the sections of the border which you can observe. And now assume that and this is the Bayesian part of the game. So there's another degrees. Now assume you have 2 possible types of the attacker. Let's call them the low profile and high profile, and assume that they are, human traffickers. And high profile simply gives you a much larger loss since they have much bigger groups, but they have the same strategy space. I mean, the attacker of each type can either choose one of the 4 sections or to resign from an attack, right? So they have a 5-element space of strategies, and you can see what your plays or combinations of pure moves will be. So basically, depending on the whether you have a high profile or low profile attacker, then the utilities will increase with SI. So let's assume, for the sake of example, that for high profile attackers you have for S150, for S2 100, for S3 150, and for S4 200, right? And divided by 5 for a low profile attacker, and take the payoffs of the defender to be simply opposite, and add some random noise to it, so that you don't have too smooth results. Basically, that's the model, an example that the team chose. And now assume that you have the higher probability for a low profile attack and the lower probability for the high profile attack. Then let's skip the calculations, but you are able to compute that an optimal mix strategy for the defender is simply to play the protection of the sections S1 and S3 and S2 and S4 with probability 50% each, right? So in particular, you never have, for instance, sections S1 and S2 protected simultaneously. And then if you consider like simple Stackelberg equilibria, you can easily exploit that by performing a 2-phase attack, right? You obtain an information about that, and then you attack one of them, and you be able to do a second phase attack to do much bigger harm, right? So you can breach 2 sections of the border in distinct phases, S1 and S2. And to see that, you can actually consider the scenario where you have now first a low profile attacker that makes an attempt to breach the section at the border at section S1. You have the information from the initial phase of the attack because you know the conditional probability distribution with respect to the defender's resources, and you can use that, right? So in order to model that, we might want to adjust the defender somehow, right? I will, for the sake of time, I will skip the exact calculations. And 2-phase attacks can simply significantly alter the Stackelberg equilibrium of the game, and it can change the optimal strategy of the defender to be made into, basically it will smoothen things out. And the thing is that the two-phase Stackelberg equilibria will be in general more robust against changes of attacker profiles, and you can obviously use this model to try to compute algorithms based on Stackelberg game solvers for other spaces of applications for protection of critical infrastructure. So I will skip perhaps the exact tables with calculations for chance of two-phase attacks and get to the summary quickly. So in essence, what I wanted to convince you to is that there are indeed some methodologies to ensure the safety of critical infrastructure. And I didn't speak anything about the optimization techniques and the way and the algorithms of AI are being used and incorporating that, but my main focus was the game theoretic tools. And actually, those methods have been successfully deployed in practice in multiple locations, for instance, in the United States. And the thing is that they were achieved not by buying new patrols or hiring new people or buying new technology, but you basically optimally deployed the available resources. And a little bit of advertisement for the very end. In our team at the Research Institute, we want to basically extend those results and make them really applicable to various types of critical infrastructure in Europe. And if you wish to read a little bit more about that, we have an expository paper that's been published by the magazine of the Polish special service called Internal Security Agency. The journal has a very funny name: Terrorism Studies, Analysis, Prevention. And there is paper is both in Polish and English, so you can read the English version to find out more about the particular applications, about the particular deployment in the States, and about particular ideas we might have, we might want to have, and the specific applications that are in a sense in need quite currently in the real life. So I would like to, I skipped the time. I crossed the time by 7 minutes. I would like to apologize for that and thank you for your attention.
Hi, can we do any question?
I would be honored.
So do you see any benefit of using a weak Stackelberg equilibrium instead of the strong?
So you mean that instead, I will go back to the definition. So you mean this one, and in the weaker one, what do you change?
So you assume that the follower, if there is any tie, you choose the worst strategy for the leader.
Yeah. No, so the best strategy for the leader.
Yeah. But no, but in the weak.
In the weaker one. I mean, I would guess that the application, so the applications in such case would be in essence similar, but what my opinion would be basically is that it depends on a particular application. And the thing about this type of work, when you really apply it, is you really have a toolbox and you choose from the toolbox depending on the application. So I wouldn't be dogmatic about having Stackelberg equilibrium better modeling that situation. If you have a situation where you have a defender and they have a particular incentive not only to maximize their own payoff, but additionally, if it's possible to diminish the payoff of the opponent, then that would be the situation in which the weak Stackelberg equilibrium would be applicable. And I think that there is literature about that on the malicious players in game theory. So I would say that I wouldn't tell you right offhand what kind of applications would that would be, But I imagine that if you consider a particular scenario, like for instance, that the railroads come to you and they order a system for protecting train stations or something, then you consider which kind of equilibrium is more applicable. That's why I also said that sometimes in security domains using Nash, I don't remember which slide it was, using Nash equilibrium and computing the best or the worst Nash equilibrium might be actually useful. So I don't know if that's a satisfactory response.
Yes, it is. Thank you very much.
Thanks.
It was a very good response and a very good talk. I work in similar topics, but only from the optimization point of view, not artificial intelligence.
From what point of view, excuse me?
Optimization, just optimization, not artificial intelligence.
Okay, perfect. Thank you. I'd like to talk more later, perhaps, if that's
for sure. I also have another question, but I don't know if you have more time.
I mean, I do. I don't know about. Basically I cannot see you and I cannot see other people. So that's actually a question maybe to the organizers.
You still have 10 minutes.
Okay. So in the case of this two-phase attack, do you see this as a one level or two level model or other kind of model in this two-phase?
What do you mean by that? One level or two level?
Oh, because for example, from an optimization point of view, we usually the Stackelberg Security Games, at least what I have seen, is that, for example, this is a B-level game, but sometimes you just work with one level. So you do some things in order to just work with one level and not B-level. So in this case of two-phase, do you see it as B-level programming or as just one level, like a normal optimization?
In the sense of linear programming. So So I will give even more disappointing answer to that. Andrzej Nagurko is the optimization guy in the team, and I think he said he wouldn't be here, and I don't see him. But that's a question that I can address to him, because I really don't know whether in terms of programming whether that's one level or two level.
Okay. Yeah. Thank you.
Thank you.
And the other question was, how do you know if the two-phase Stackelberg game really lets you obtain a more robust solution? Because at some point you say that the solution for this two-phase was more robust. And
so
how do you know this?
So in this sense, when you have one phase, then you have an optimal solution that's kind of silly in a sense, and then be exploited by the attacker. And in real life, you will not do such a thing. Basically, you won't decide on this particular mixed strategy because it is silly. So in a sense, modeling by one phase Stackelberg games is inaccurate, because that's not the way the notion of rationality that you're aiming for. And when you get with obviously with examples of quantities that you have, you might have a much more reasonable strategy going two-phase instead of one phase. So in this sense.
Okay. And just to be like super clear, if I understood, two-phase means that there are two attacks, like one after another?
Yes, in a sense, yes.
Okay. If nobody else have a question, I have just a curiosity question. When you say that you are working with instances that have a random noise, why is that? I didn't fully understand. Sorry.
So that because if you didn't have that, then I think we were afraid that the computations would give us results that are deceptively too smooth, so that when you have payoffs, so structured, and then you would have exactly the opposite payoffs, then you would obtain two unrealistically smooth results for some combinations, I think. And I think that was based on some simulations that Andrzej did with respect to the particular tables of examples of probabilities of attack.
Okay. Thank you.
Thanks.
Sorry, I have another question. Have you ever seen like the reinforcement learning for this kind of problems?
No, I actually have not, and that would be very, very interesting. I'm sure that there have to be examples of that, but I haven't seen.
Yes. I still haven't worked with reinforcement learning, but I think that it should be like super useful. I have seen some people that were only working on optimization, that they are now using reinforcement learning for this kind of problems. So I think that maybe it could be useful.
That's what, yeah, that's one of the things that we would also like to have, but in not so far future, but in the future. But that's I think one of the steps to make, basically.
Yes. And now when you say that, when you mention artificial intelligence algorithms, you are thinking of what specifically, or is like more general?
For that, it's a little bit more general. There is some ML in some simulations that is being applied, like in the systems that are deployed in the US. But I don't think that's anything fancy compared to the current technology stack of the possibilities of AI.
Okay. Thank you.
Thanks.
Yeah, thanks, Michał. We
Thank
didn't
you.
die off here. It's just we had some problems with mic. So, but I don't know. Can I just quickly ask a question? So, here we kind of assume that the attacker can have a perfect knowledge of our distribution, but then it seems that we can profit from assuming that he just has some samples from these distributions. So not, I mean, and he kind of want to do just an optimal response, knowing that our distribution is in some range that he knows from this sample.
That it's in some interval. Yeah. So the model that I depicted doesn't employ that, but when I said about the imperfect rationality, that was not only the strict sense of imperfect rationality in game theory, but also that. So when it is being deployed, you've got some range of uncertainty about the particular distribution, also in the in the performance of attacker. But that is a very good remark. It is indeed that when you have samples, you have to, as I said, extrapolate the distribution.
Yeah. Okay. All right. So I guess let's wrap up. So thank you very much again for the talk.
Thank you so
Hope
much.
that we will. So, okay. Thanks all, everybody. See you.
Oh, and I would be happy to share the slides where I also have the link to the paper, and I would be more than happy to stay in touch with anybody who's interested and talking about I don't know,
Yeah, I
further
hope
work
we
or
can
collaboration
just
or whatnot. Yeah. So
probably we
would
can
that
just
would be great.
share the slides of your slides on the mailing list, right? I think. Yeah. Okay.
Perfect.
Yes, and
We
the
will do that.
mail, if possible.
Yes, of course.
Okay, thank
So
you.
I will. I think I didn't have my email address in the slide, so I will add that.
Yeah. Okay. Super.
Before I share the slides.
Okay.
Thank you
Thanks.
so much.
Thank
Thank you.
you.
Thanks. Bye.
Bye. Thanks.